All right, welcome everyone. Once again, thank you all for joining the session today. My name is Matt. I'll be leading the presentation today. And what we're going to be speaking about is some of the newer capabilities that are available in S-TIMBER. If you're not familiar with S-TIMBER, we do have a slide that we'll be going over the software with. We're not really going to be talking about how to use the software so much as some of these new technologies, including the generators of different types of loads, different types of connection design checks, which we'll go over, how to define things like panel edge connections, and then member design. Now, during this presentation, you're more than welcome to ask your own questions. You can type them into the Q&A field. We'll do our best to answer these questions as we go. Whatever we can't respond to, we'll do some follow-ups after the presentation, and we'll try to respond to those then. Now, my name is Matt. I work within the global technical team within Altair, specifically focusing in on the AEC applications, primarily the S-Frame suite, but more recently other tools as well. And I'm really excited to show you what's come out of S-TIMBER in the last little bit. So if you're not familiar with S-TIMBER, it's really designed as a mass timber analysis and design software, but it does do quite a bit more than that as well. You'll notice right away, if you have never seen the software before, it has a very intuitive interface, and it's very customizable. So you can dock your windows wherever you want. You can set up your defaults quite nicely and really tailor it to what your specific workflows might entail. It also offers a parametric modeling environment, and some aspects of that that are relevant to timber design would be the generation of rigid offsets when you have large section sizes of members that are connected at their center line, for example. It may also involve the creation of different types of objects that are collectively defined or grouped together different smaller components like a shear wall or a floor diaphragm that might have a number of different elements within it that can be defined and edited parametrically. S-TIMBER is using S-Frame's finite element analysis solver. If you're not familiar with S-Frame, it is our general structural analysis and design software for the AEC market, focused on structural engineers. And it's been in industry and battle tested, I suppose you could say, for over 40 years now. I think about 43 years. As far as the design goes, S-TIMBER is really focused on the design of CLT, glulam, sawn lumber, and more recently, we've also added steel design as well. And specifically to the Canadian and American timber and steel codes at the moment. We're looking to expand that, but that's what's available at the moment. Another unique aspect of S-TIMBER that might differentiate it from some of our other tools is the integrated Python scripting interface. So this gives you access to the API of S-TIMBER through that integrated Python scripting window. So if you wanted to automate certain tasks or customize workflows, really the world is your oyster when it comes to those sorts of things. You can really tap into more potential of the software. I'm going to jump right into the presentation now, and where we're going to start is with the load generators. And there's been quite a number of new sets of load generation capabilities that are added in the software. What I'm going to focus in on the next presentation here is the response spectrum load generators available for a variety of different building codes. And with that, you can also generate or extract equivalent static or lateral force or loads from those RSA cases. So you can generate those cases and extract the equivalent static loads as well. It's not limited to just those equivalent static and RSA cases, however. You can also define time history loads, whether they be nodal excitations, where you have a specific node that might be shaking, perhaps it's moving or it's being pushed a certain with a certain load magnitude that can be done, or your base of your structure is actually shaking with an accelerogram that's defined by you or one of the defaults that we have in the software. Now, to demonstrate this, I have a presentation. Now, I'll be fully honest with you. I have recorded this ahead of time just because I have quite a bit of content to squish into this presentation. And this allowed me to fit it all in if I made a video. So I'll be narrating alongside the video, but just give me a second here to set that up. Bear with me for 1 minute here while I change my sharing here. Okay. So I'm just going to play this video here. This is basically a walkthrough of some of the seismic analysis capabilities within S-TIMBER. And you can see here, this is the multi-level structure that we're going to be working with. And what I always like to do when I'm running any type of dynamic analysis is start with an unstressed response, or unstressed vibration analysis, rather. This provides us a good basis for the understanding of the dynamic properties of our structure, the mode shapes, the mass participation, and so on. So we can set up whether it's a stressed or unstressed vibration analysis. We choose how many mode shapes we'd like to extract, and we can choose the method for those eigenvalue extractions as well. I'm going to go with the subspace iteration method, and I'm asking for 10 mode shapes. And I can set up this analysis to run. You can see here it's analyzing. And once this is done, we can look at some of the results. So I'm actually going to jump down to the spreadsheet window, which if you're an S-frame user, you can think of this as the equivalent of a combination of the spreadsheet window and the numerical results. We have both of pre and post processing data available. And I'm looking at the frequency spreadsheet. And this is showing me all the different mode shapes that S-frame solver calculated. And alongside that, it's showing me the periods, the frequencies, mass participation factors, and so on. So you can see the first mode has a period of about 0.3 seconds and not a lot of mass participation in X or Y axis, about 16% in the Y axis. The next mode down has quite a bit more mass participation in the X axis, about 85%. And most building codes will require that you have a certain threshold of mass participation if you sum up all these columns. Usually it's about 90%. So you can see here, I'd want to make sure that I'm meeting that threshold. And it's not until I get down to about mode shape number 5 that I get to that threshold. And I can animate these mode shapes. So in this case here, I'm looking at mode number 2, which was my X dominant mode. And you can see here how it's oscillating based off of the values that were calculated by the solver. Mode shape number 1, which again didn't have a lot of mass participation, particularly in the X axis, is more of like a torsional mode, if you will. And so this just helps us understand how the model, how the structure is oscillating and the dynamic characteristics of the structure. Now, to work with our seismic analysis, it's helpful to set up stories. So I'm going to generate some stories that can be done automatically for us. And it's going to specify how many stories I have and the story height. And if we had some variance in our floor height, we could set up a tolerance, and then I click OK. Now it's generated those stories for us. It went through that a little fast, but then what we can do next is we can specify our RSA curve. So I'm going to go to the building code definition. I choose which building code I'm using. And this is actually a step ahead of where I thought I was, where we have our different inputs for the equivalent static force procedure, our max periods, our ductility, and overstrength modification factors, and more. Now I can go ahead and define the different load curves that I want to use, or loading functions. So I'm going to go to this loading functions field. I'm going to specify my response spectrum function. So I'll click the add button to create my new curve. And we have this field that allows us to specify it either in a tabular format, or we can use the auto-generate option and choose the building code we want to use and fill out these different values from our seismic hazard calculator. So I'm just filling this out here, and you can see underneath the curve is being updated. And on the right-hand side, we have the tabular format. Note that it's using the units on the y-axis of meters per second squared, not the ratio of g or gravity. So just keep that in mind. If you see a value of 11, that's not 11 times g, that is 11 meters per second squared. So now I've got this curve defined, this RSA curve, and I can actually create some load cases and apply this to my model. So that would be the next step here. I'll go back to the define menu, go to the load cases, and I'm going to create a new load case since there's not any existing load cases in my model. And I can change the type of load it is. In this case here, it's going to be a response vector load. And I can give it a name. I can then start assigning my response vector. I just have one in this scenario, so it's not too exciting. I just have the one to assign. We can also choose which direction we want this curve to be in. I'm going to say it's in the x-axis, so I give it a factor of 1 in that direction. And just above that, you'll notice here we have inputs for our modal combination, our spatial combination, and a critical damping ratio. I'm just going to change one of those. The critical damping ratio, I'm going to change to a ratio of 5%. So apply this. I could also click OK. It will apply it and close the window. And now I'm going to go ahead and run the analysis. So the analysis I'm going to run, previously it was an unstressed response or vibration analysis. Now I'm going to change that to an unstressed response spectrum analysis, which borrows a lot of similarities from the vibration analysis I already ran. We need to run a vibration analysis to get this to work. So I can choose how many mode shapes. I'm going to stick with what worked before, 10 mode shapes, because I had enough mass participation from those mode shapes. And you'll also notice just above there, we actually have another field where we can define different properties related to scaling our base shear and so on. I'm going to keep it as do not scale for now, but we can always play around with those if we want to. I'm going to go ahead and run the analysis now. This is running an unstressed response spectrum analysis, which will first run a vibration analysis. It will determine all our mode shapes, and we'll be able to interpolate from that RSA curve the base shear and other properties for our analysis based off that information. So here the analysis is completed. You can see we've got here, I'm just showing a deflection plot, which doesn't have too much to show me right now. But what I can do is go back to the numerical results, specifically the response spectrum results that we just calculated. I want to look at the base shears. So I click on the base shears spreadsheet, and this is showing me the base shear from that RSA load case, but I can also look at it on a modal basis. Because remember, with an RSA, we have to combine all these different modes together. So we can look at individual modes if we wanted to as well. And that's what I'm doing here. I'm looking actually at all of them, but in different rows, we'll have different modes. And not surprisingly, we see that mode number 2, which is our dominant mode in the x-axis, has the highest base shear because it has the most mass participation in the axis that we applied the load. I also have other results available, like the story drift, which you can see is pretty low in this case. And I can look at things like story forces and so on. Depending on what it is, I can oftentimes find a pretty good readout of that information in this result spreadsheet. So now that we've calculated this, let's go ahead and extract our equivalent static loads, which can be done either just for lateral loads, just for torsional loads, or we can extract all the torsional and lateral loads that we need. So I'm going to click on this option here, and I'll just choose the RSA case because that was the only one I had, RSA and X. So we're going to generate those equivalent static loads. And I can actually go here to the load case spreadsheet, and I can see it's generated these 2 extra load cases. So one of them has lateral force plus the torsional force, and the other has lateral force minus the torsional force, looking at different directions of torsion. And I can actually see those magnitudes here as well. So if I go to the joint point loads, I can see the magnitudes of those forces and what they are throughout the model. So this is showing me torsion and axial load in different load cases. Now I'm going to go ahead and run an analysis, but this time rather than running an unstressed response spectrum analysis, I can just run a static analysis because I have that static load case or those static load cases. And that allows me to then combine those with other load cases and perform design checks without having to run an unstressed response spectrum analysis. And I'm sure many of you are already aware, but one of the downsides of running an unstressed response spectrum analysis is due to the statistical means used to combine those different mode shapes together, we do lose some of the positive and negative signs for things like joint displacement, which makes it hard to really know what our deflection diagrams will look like and so on, whereas this extracted equivalent lateral loads will allow us to see kind of more perhaps realistic view of that model without that downside of the RSA. So here's the deflection diagram or the deflected shape here. And you'll see in just a minute now we're going to look at some of the member results. So here's a deflection diagram, but I'm going to actually look at a force diagram. And we can look at axial forces, for example. We can imagine that our bracing is going to be doing a fair amount of work to resist those loads, specifically the x-axis bracing. And I can actually drill down into the member results on the right-hand side. And I can look at my trusses, for example. And I can actually select individual trusses or a set of trusses or the whole truss group and see basically an envelope for all that data and see the bounds for the maximum and minimum loads on those trusses. So it's around 495 kilonewtons in the negative and positive side. And I think that's the end of this video here. So let me just jump along back to my slides here. Give me 1 second to get everything back. Okay. The next topic I wanted to bring up was connection design. And this is another new feature that we're quite happy about in S-TIMBER. The ability to basically calculate the forces on our connections, but also perform design capacity checks on our connections as well. So this starts with the definition of a connection or a connector, and also the connections themselves. So we have basically a definition of connections at our joints, and we can control the orientation of that connection relative to the actual object that it's going to represent. And from that, we can calculate those design forces from that summation of member end forces. So we choose which members are contributing to a connection. It could be one, it could be multiples. And S-frame will calculate the member end forces and sum them up in the orientation of our connector. So here's an example here where we're using the connection tool, and we can give it a name. Depending on what it is, we may want to give several different types of connections, and we choose which member is contributed and in which member is going to be the secondary member, and we click apply. Now that connection occurs, and you can actually see that rendered graphically there. And I can select that entity, and we'll be able to control it from there as well. I can assign different coordinate systems. So if I want a coordinate system that is perhaps unique to the slope of the member, I can set that up, or it could be relative to one of the other coordinate systems or the global coordinate system if we wanted an orthogonal type of connection. Then we can go ahead and run an analysis on this. And what it's going to do is it's going to look at the member end forces going into that connection and present that relative to the orientation of that UCS that I've defined. So this is showing me basically the connection design forces for that particular location in that connection. And to take that a step further, we can actually apply connectors to these connections as well. So you can think of the connection as like the sum of the members that are contributing to that connection. But the connectors are actually the physical object that is going to be transferring that force. And we can perform code checks on these as well. So not only are we calculating the connection forces, but we're actually performing demand capacity checks on the connectors. And we can define these as user-defined connectors. We can also have databases. We have one that actually ships with the software. And you can define your user databases in a CSV format. So it's easy to basically bring data into the software for that type of purpose. And this is the video here. Let me just quickly show you here. So it's a different connector or connection than we were looking at before. You can see here that we've defined this beam hanger connection. And we know the forces on that connection from the analysis. So what I can do is I can go and define a connector. And that can be my own custom connector where I give it a unique name, and then I define the relative properties of that, the capacities and different orientations, or I can actually import it from a CSV file like we mentioned. So here we've got an example here, an MTC beam hanger, where I can choose a connector that I want to import or a set of connectors that I want to import and apply to my model. And you'll notice that they have the properties already filled out. So it's got the capacities, for example, and then I can assign that to a specific connection. So I could say, okay, I want this particular Raycon connection to be assigned to this connector to this connection rather. And when I perform the analysis in code check, not only is it going to calculate the connection forces, it's also going to perform demand capacity check on that to make sure that we're not exceeding the stated capacity of that particular connector. So here we can see it's actually looking at member results here, but I have this connections checks option where I can look at the connection capacity, demand capacity utilizations for any specific loading condition that I've ran. And this is what we can see here on the right-hand side. And again, those connectors, we have an example that we've imported, but they can also be defined as a CSV file. So we could go in and say, let's just open this file and see what it looks like. So this example sample that comes shipped with the software can provide a good template to basically facilitate this yourself. The one aspect that we haven't really touched on yet is the definition of panels, and maybe more specifically, the interplay between the different panels and other objects. So we've allowed for the definition of panel edge connections, which has been a popular request from S-TIMBER users the last little while. And where we see this perhaps having the most value right now is for CLT panel connections, where you can control basically the panel connections to adjacent objects, whether that's other panels or members that are supporting it, for example, a variety of different applications. And we can define the different connection types. So it could be fully detached, meaning that while these two objects do come into contact with one another, they're not actually connected. So the mesh controls are going to say that it's not transferring any forces between each other. We could also say it's pinned, so there's not going to be any rotational restraint or connection between those objects at that location. It could be a rigid connection or some sort of custom connection of your choosing, where you choose which degrees of freedom are going to be transferred from one object to another. Now I've got a demonstration for this. I'm just going to bring up my file here. Give me a second. Gotta find the right data I have here for this. I'm getting a little too far ahead of myself here. I have a new monitor and some things were popping up on different screens. Okay, so this is the file that I wanted. You can see here what we're working with. Maybe just for a little bit more detail, we can see from framing view, if I just make the CLT panel transparent, I basically have these 3 glulam frames that are supporting this CLT panel. Or sorry, 2 CLT panels, longitudinal panels. And these are aerial load panels. So if I go to the physical element view, we can see here what they're looking like. And they have different spans and so on, but really what I'm interested in here is to define the connection between the members that are supporting this and the panel connection themselves. But just to introduce this a little bit more, let me just introduce my loads. So here I've got just one load case, the dead load case. And you can see here that if I select it, it's basically just a 5 kPa load applied to each panel. Now I've got my default conditions here, which is assuming that there is no pins between these connections. So if I look at the finite element model, you can see here that we have a shell element mesh representing that CLT panel, and it's connecting to this beam, for example, on the left-hand side, in the middle, and on the right. You don't need to remember all that, but let's just look at the results from this if I go ahead and run the analysis. And this will be kind of our starting point. So you can see here, conveniently it's showing me torsion right away, but let me just show you the deflection shape first. We can see how it's deflecting, and basically it's draped over that frame or those sets of frames. But when I go back to the member forces tool, what we'll notice right away here is that we have torsion on these beams here that are crossing and supporting our panel. So that's indicating to me that there is some moment connectivity between the panel edges and the beams that are supporting them, which may not necessarily be my desire. I might want to do that a little bit differently. So what I can do here is I can go to the object view. And what I want to do now is I want to click on this connection tool. And you saw this in the last set of slides, but we have this option to do the connection type is either a member or a panel. I'm going to go with the panel option. And I can choose the connection type. So here, let me just choose the pinned option. And what I want to do is basically define my panel ID. I'll just click on this one, and I'll just use this panel for now. And I'm going to define the secondary member, which is going to be this member right here. So it's identified that member, and I'm going to click apply. And it might have been subtle. You might not have noticed what happened here, but if I go into the physical element view, we can see that there's a little blue line indicating that something's changed about this particular member. And I can go to the finite element view, and I can actually see now we have these constraints that are basically saying that we've generated a duplicate set of joints to detach the rotational degrees of freedom at those specific joints in the member from the equivalent joints in the mesh. And I can continue doing that on the other members as well, just doing a similar command. So I'll just do it for a few just for the sake of demonstration. I'll select my panel, and I select my secondary member. It's identified those here in this spreadsheet, and I can click apply. I'm going to do the same thing. I'll do it one more time. This panel here and in this member. You'll notice here that we've got this little line that indicates the presence of a member there and the connection between them. I'm going to click apply again. And the finite element model, you can see here we have those constraints defined. The same data can also be found in the spreadsheet. So if I go to the TIMBER spreadsheet, or sorry, the geometry spreadsheet rather, I can look at the panel connections and I can see the connection type that's listed, the primary panel ID, and then the secondary object ID. In this case, it's a member. So let's go ahead and rerun this analysis. So I'll just shrink this panel down, which we could always hide these windows on other monitors, but I can only show you one monitor at a time. So I'm going to keep them all in one, and we're going to reanalyze this. And you can see here, it's split into two, but on the left-hand side of this view, further in the y-axis, we're not getting any torsion on that particular connection. Now, I could have done the same thing on this side of the model as well, but I just chose to do it on one side just to illustrate to you the differences between these types of setups. So that's something that you can take advantage of if you have beams that are connected to one another, beams that are connected to panels, and you want to transfer those forces, or not transfer those forces depending on your applications. So I have another model that I want to show now. This model here, it's going to load it up. Oh, that's not the right one. Just make sure I've got the right file here. Okay, this is the file I was looking for. And you can see on the surface, it does kind of bear some resemblance to the previous model that we were looking at. The main difference between this is we don't have an interior frame. And what we have instead is basically two different CLT panels. And this is really to illustrate the connection difference between a pin connection and a non-pin connection in a continuous CLT span, or discontinuous in this case. So what I've done here is set this up with similar types of loading. So I've got basically 5 kPa on both sides. Again, these are represented by shell elements. So if I just look at the shell element mesh, we can see we have a fairly fine mesh between those. And I'm going to go ahead and run an analysis just with the starting point that I have right now. And what we should expect to see, and I think it's most obvious if we look at the deflection results, is we get basically the same sort of behavior as if this were just a single piece of CLT that was spanning between those. It's going to start to sag in a pattern that we might expect. We can also look at things like our panel contours. So if I wanted to see the panel contours, or perhaps maybe the strip lines, I can look at those as well. So this is showing me the moment contours, but the strip lines might also be of interest. I've defined a custom strip line along the center here. And it's very clear to us that we're getting basically 0 moments at the ends, which is great. But we're having, in between the ends, we're having a spike in moment there. Now let's just say what happens if I were to define a pin between this panel and this panel here. So I'm going to do the same approach. I'm going to use the connector tool, the connection tool rather. Change the connection type to the panel connection type. And the connection type that I want to use is a pin connection. I'm going to left click on this panel here and left click on this panel here. You'll notice it's identified that shared edge between the two. And I'm going to click apply. Now when I look at the finite element model, here we can see something very similar to what we had before, but it's basically generated these duplicate sets of joints again that can represent that pin constraint line behavior between this. We have a similar concept in S-frame if you're familiar with S-frame. So now I'm going to go ahead and rerun this analysis. Click analysis. And you can see here, maybe I'll start with the deflection diagram. Clearly, it's much different than what we had before. And I think this is to be expected. If we have a pin, we're naturally going to have that kind of kink in this line where that pin occurs. Now, you already got a bit of a preview of the strip line results. So this is showing me the moment along the center of this, this panel. And I thought it was pretty interesting just seeing the different moment diagram behavior. We can clearly see that there's a 0 moment kind of inflection point here at the connection, which I think makes sense. And we're seeing here the shorter cantilevered panel this panel on the left here, is also seen to provide some sort of almost vertical support to the longer one, as we can see from this, this type of moment diagram. So it gives us the ability to study this perhaps behavior in a different light. These aren't behaving like concrete slabs that are one continuous kind of monolithic object. They are behaving as individual panels that are connected in the way we decide them to be. Let me jump back into the slides now. Where did they go? Oh, I got a little too far ahead of myself. Okay, member design. This is the last section of the presentation here, and I think this is another exciting one where you can basically use S-TIMBER as a tool to size your sections. So if you have timber or steel members, much like you can in S-Steel, for example, you can run an analysis with your sections, and you can either perform a code check, which S-TIMBER has done for quite a long time, basically validating that the section sizes you're using are satisfactory according to the code provisions. But you can also now do a member design. So this involves the definition of design groups and section lists, where you basically group different members together. And those members can be grouped together based off of constructability, perhaps the ability to source different sections and so on. You don't want to have too many different cross sections in your model. And you define design groups that basically group members together. So maybe all of your columns in one part of the structure, you're going to assume have the same cross section. And regardless of if one of those columns has a higher utilization than the others, you want to use the same cross section for constructability, maybe for architectural purposes. The list goes on. But you can define those design groups and then allow those design groups to have different section lists associated with them, so that when you run an analysis and you find that a section might be overutilized, you can then have S-TIMBER go in and choose a new section from that list for that specific design group. And you can define a bunch of different criteria to optimize based off of as well. So I'm going to go into S-TIMBER again, and I'm going to open up a file. Just open this one up here. Not going to save this guy. So this file that I'm working with here is utilizing a few different aspects of some newer features in S-TIMBER. Obviously, the member design that we talked about. It's also using area load members and area load spans, which we'll talk about in just a second. Seems like it's taking a minute here to load. But you can see on the surface, it's really just a 3D frame. In this case here, I've got very small glulam members assigned, and that's on purpose. But if we look a little bit deeper at this, we can see here that we've got area load panels set up for this particular set of CLT panels. And I've deliberately set them up differently. So we can define span directions on each panel, much like we can in S-Frame. So in this case here, I've defined a one-way span in the long direction, or in the short direction rather, for the models, the panels on the left-hand side. So basically, any area loads applied to this panel are going to be shed to this longitudinal member or this longitudinal member. And the same thing on the panel right next to it. But on this other side, we're going to have a two-way span. So basically, any area loads applied to this panel or this panel are going to be shed based off this two-way span definition. So the tributary area of each member is basically shown with these green lines. And the intention here is that I'm going to end up with quite a few different sets of magnitudes of member loads that I'm going to be working with in this example. And when I do this, I can also look at the member loads that are generated from these applied loads, and I can see here how they look on the model. I can actually display their magnitudes. In this case here, I'll just left click on it and I can see the magnitudes that are being used. It might vary from member to member, but as you can see here, we have a variety of different loads. Now, my first goal is to actually set up some design groups. I want to use design groups as a way to group members together so that we can have an efficient yet practical design. And different loads on each member, that's going to mean that if we were to design each of these members in isolation, their optimal section might vary from member to member. But as I mentioned earlier, that could be problematic for coordination of construction and design. Obviously, it's going to be a little bit more challenging to put that all together. So for this reason, we're going to specify design groups that group members together to ensure that they are going to have the same cross-section regardless of their utilization. So to do that, I can go to the Define menu, and I'm going to go and set up a couple different design groups. So we can see here we have this option under Define for design groups. And I don't have any defined yet, but I'm going to create a couple here. So I'm going to click on the Add button. And I'm going to first start by giving it a name. So I'm going to call this one column. And I'm going to define the member types as a column. The material that I want to use, I'm going to say it's glulam. That's what material I currently have. And I've actually already specified a couple section lists. I'm going to define this column section list. And I'm just going to dive into this a little bit more. If I click on this ellipsis button, it's going to load up section lists. And specifically, I want to look at the timber section list. If this just opens up here, I think WebEx might be taking a bit of my bandwidth here today. You can go a little slower with this model, but basically it's a list of sections that we've assigned to be considered for the design of our columns in this case. Where did my timber go? I think it just hid behind there. So here's my timber sections. I actually have two different timber lists. And I'm looking at my column section list. We can see here that we've assigned all these different glulam sections to be considered. Now, we wouldn't necessarily always need to have that large of a section list, but I've chosen to just for this example. And I'm also going to assign the starting point section as a glulam 80 by 114. I'll click the Apply button. And I'm going to do this and create two more section groups. They're both going to be for my beams. I'm going to call it Beam X. And I'm just going to apply the same details here. So it's going to be glulam material. And I'm going to use the beam section list, which is very similar to my column section list. And my starting section is going to be the 80 by 114 glulam section. And lastly, this third and final one is going to be called Beam Y. From here, we're going to define, again, the same properties. Glulam, and the section list is going to be from my beam section list. And we're going to use glulam 80 by 114. So I've got these all assigned now. And the reason I chose that 80 by 114 is that's going to be our original starting section for the design. And it happens to match the applied section I have for each one of these design groups. And now I can go ahead and start assigning section design groups to each one of these members. So I'm going to change to my framing view. It just makes it easier to see everything. And using the selection tool, I can just left click, make sure I've got everything, select my members, and this members selection tool set here, I can define the design group. I'm going to say this is my column group. They've been now assigned to that column group. I'm going to do the same thing for the beams. So these beams are in the x-axis, so I'm just going to select those. And this design group is going to be Beam X. I'm going to do the same thing in the other axis. I have Beam Y. And while nothing has changed on the surface, we're now able to see that we're getting some assignments of our design groups. So the first thing I should do is actually run a code check on this model, because I haven't actually checked to see if my sections are over or underutilized. That might be a good starting point. So I'm going to go ahead and run the analysis and code check. Just a linear static analysis. And we'll be able to get these utilization ratios out after we run the analysis. And I'm expecting these members to be failing. I've deliberately assigned them small section sizes, but as you can see, we have quite a variety of different utilization ratios. So the point to remember here is that our design groups have been set up so that whatever member has the highest utilization in that design group is going to be driving the section choice for that entire design group. For example, for my columns, you can see here that I have a range from 0.53 utilization to 3.09. So naturally, this 3.09 section is going to be the weak link in my design group for the columns, and that section selection is going to have to satisfy all the demands of this particular column here. The same goes for my beams. You can see I have some pretty long beams with from high loads and some that are quite lightly loaded relative to that. So we would need to consider that. So we have the design wizard that basically allows us to let the software choose new sections based off the design group settings and the section list that we've assigned. So I'm going to let the software do its work here. I'm going to go to the Run menu. And I'm going to go to the design option here. And you can see we have a few different options. I'm going to go with the timber member design. And we have this option to run design. So here I'll click Run Design. And you have a few different options for defining the design method, whether it's the one that meets all your criteria or the list of the section list that you have. I'm just going to say, let's go ahead and design all of these different design groups. I'm going to click the Run button. And it's running the member design, but right away, you're not going to see any differences. However, what I can do is I can go to the spreadsheet view here. And under the spreadsheet view, we can see here that we have some design options. And I have this member design field or selection that I can select. And this is showing me the design group. This is showing me the currently applied section. And for each design group, I also have a design section. So it's found for this particular column group, the original utilization was 3.09, but I can get down to a utilization of 0.7 if I use a glulam 80 by 228 section. For my beams in the x-axis, I have a higher utilization. And this is going to say that I can get down to utilization that is just below the passing limit if I go with a 80 by 266 section. And the same thing for my beam in the y direction. It just doesn't have quite as large of a section because the loads aren't as high there. So I can choose to use those design sections. I can also override the design. So if I don't agree with what is selected here, I can say, okay, let's just override this and let's see what happens if I go with perhaps a different size section. Now we're at a pretty small section size right now from our list, but maybe if I go up a section size, the design utilization is going to change. This is all based off of the selections within our section list here. I'm going to choose not to override the design and just going to have faith in what S-TIMBER has selected for me. And if I go back into the Run menu and back to design here, I can go back to Run Design. Oh, sorry, not Run Design. I'm a little bit ahead of myself. Timber Design. And this time I'm going to say, let's use our design sections. So I can choose what I would like to use for my design. If I want to override anything, again, I could do that here. This is the same controls that we have in the spreadsheet view. I'm going to click Apply. And you can see now S-TIMBER has updated my sections with these new section sizes. And I could go ahead now and run an analysis and code check. And the point to remember here is that the original analysis results that were used for the utilizations that we saw earlier were based off of those small section sizes. Naturally, when we run the analysis, our self-weight is going to be considered. The stiffness of each element is going to be considered. So we can get some variance in terms of the original utilizations with these proposed sections versus the final ones when we actually run the analysis on the updated model. But what we can see here is that we're still passing these code checks. We could generate a report if we wanted to, and we could be satisfied with that design. Obviously, we can override it as well, but it gives us a really good kind of understanding for what size sections might work. So that brings me to the end of the presentation here. As you saw from S-TIMBER, it's available to do mass timber analysis and design, but it can actually just do general structural analysis and even steel design as well. Some of the newer technologies that we've added to this allow you to look at the utilization of your connections and also calculate the forces going through your connections. It can also allow you to generate a variety of different types of loads, whether it be seismic loads, wind loads, or load combinations, or load cases. And being able to represent the connectivity between different objects, whether that's panels to members or panels to other panels, is important to represent the true behavior of your particular structure. And if you're looking to optimize your timber sections according to the code provisions or maybe other provisions that you might have specified or other constraints you've input on your model, you can do that as well automatically. And the nice part is if you're using S-Frame or you're using S-Concrete and you have access to the structural or advanced structural engineer suites that are available from Altair, you already have S-TIMBER. So we encourage you guys to take a look at it if you're doing timber analysis, or maybe you just want to try the software out. We have lots of resources available to help, and we're available to help as well. So at this point here, I'm going to open up the floor for questions. There were a couple of questions that came in. I'll do my best to respond to those live today. Whatever we can't get to, we'll respond to in the coming days via email. Just give me a second here just to catch up. Sorry about that. Thank you, Moeen. Apologies for that. So there were two questions that I tried to answer there. I'll go through them again. One of them was related to design codes. Just to recap really quickly. Under the settings menu here, if we go to design, we have this timber code setting, and you can see we have the latest Canadian and the previous Canadian 086 code. We also have NDS 2018. We're working on more codes as well. So if you are working with timber design and you want to use S-TIMBER and you don't see your code supported, please let us know which code you're using and we'd be happy to look into it. The other question here was related to something I had in my PowerPoint, so I apologize if that was not conveyed very well. But basically, what is the difference between a connection and a connector? And so the way to think of it is a connection is like the assembly of member end forces, and you can assign which members are contributing to a connection at a joint. And those member end forces are going to be calculated and summed up in a specific orientation relative to the settings that you've chosen. A connector is basically the physical object that is going to be transferring those loads in the real world, and it can have a capacity as well. So if you know that you have 100 kilonewtons of extraction force at your connector, or in your connection rather, that connector might have a capacity of 110 kilonewtons. So that would mean that you're just under the capacity of that connection, and that can be used for code checking. Another question that came up was related to diaphragms, and I see another question actually in the chat related to that as well. And whether or not you can define diaphragms as rigid or flexible diaphragms or semi-rigid. All of them exist, just like an S-frame if you're familiar with S-frame. The example that I chose, I'm trying to recall if that was using, I believe it was using a semi-rigid diaphragm approach where we meshed it, but rigid diaphragms would work as well. So it really depends on your specific scenario and what you've defined that as. Now we're getting a little bit long into the presentation. I see my colleague Moeen has helped with answering some of those questions. So thank you, Moeen, and thank you for alerting me to that, that audio issue I had earlier. I'm just going to jump right to the very end here. And actually, I don't have any more slides, but one more point I want to bring up is if you do want to learn more about S-TIMBER, a great place to look here is actually not only on Altair 1, where we have training available. We talked about that in previous webinars, but also on our YouTube channel. We have a lot of videos on S-TIMBER as well as our other solutions. So if you just search for S-TIMBER tutorial, for example, you'll find it. You can actually see our playlist of tutorials and so on. But there's other videos that are perhaps more focused and more intended as standalone videos as well. So you can find whatever type of video you're looking for here. And if you have an idea for a future video of a capability that you've heard about and you're not sure how it works that you can't find here, again, feel free to reach out. We're always interested in kind of making this more practical for you. So with that, I think that is pretty much everything on my end. I appreciate everyone's time in the presentation today, and we hope to see you in a couple of weeks for the next webinar. This next webinar is actually going to be on wind loading in S-frame. So if you're using S-frame and you need to design structures to wind load, we encourage you to take a look. And also for anyone that's interested, specifically located in Alberta, in about a month and a half, August 22nd, we're going to be holding a user day in Edmonton at University of Alberta. So if you're interested in that, please get in touch. We have sent out some emails, but if you haven't received them and you'd like to attend, we would love to see you there. So feel free to reach out. Thank you, everyone, and enjoy the rest of your day.